Despite modern safety protocols for vessel inspections, all it takes is a few minutes for things to go from bad to worse. So we asked ourselves, how can we keep you safe while meeting applicable API codes? How can we save you time? How can we make inspections better? With robotic vessel inspection solutions from Waygate Technologies. For superior NDT inspections, navigate every inch of confined space with the bike, the only magnetically wheeled robot capable of maneuvering in even the most complex environments. There is no need for rope access or scaffolding for those hard-to-reach spaces. With modules to collect ultrasonic, eddy current, video probe, or structure light NDT data. With 3D lock software, all inspection data is automatically tagged with a precise position inside the asset, while a digital twin containing all the inspection data is maintained. Entry into confined spaces no longer needs to be a major risk to the safety and health of those involved in operations, thanks to robotic vessel inspection solutions from Waygate Technologies. With the bike, increase safety while ensuring more accurate, consistent, and efficient inspections.
Hello, everybody. Welcome to our bike robotic call this week. You're today with me, Eki Zwicker, Global Head of Product Line Robotics, and with Moritz, he is the Global Product Manager for Robotics. Let's have a look what's up for the next half hour. So, topics of today is, first of all, an introduction into confined space inspection, the motivation and the drivers behind. Then we will have a deep dive into the bike robotic platform, all the features and functions we will have a look at. And then we will close up with some application areas in which the bike can be deployed. Let's start with confined space inspection. Why robotics or why confined space inspection? It's all about workers' safety. That means no human in confined spaces, no working at height. That's one of the drivers. The second driver is about automation. That means reliable, repeatable, and high quality inspection data. This is the core of inspection. And the third element is data. That means collecting data, firstly, and secondly, tagging it with the position. That means geotagging inspection data on a digital twin. These are the three main drivers: worker safety, automation, and data. Let's drill down a little bit into this topic. So what we see here is this kind of path. So typically in what you see in the gray path here, you're seeing how a human is doing the inspection. That means you need to do the planning, you need to receive your work permit, you need to go the LOTO isolation, you need to isolate the vessel. Then you're going into, then you open then you're opening the manway. Then you need to have a watchman in place in order to save the person inside. In parallel, you need to have a rescue team organized so that in case something happens, then you can maybe starting scaffolding. That means then you're preparing with this one, you can prepare for the inspection, cleaning, and then execute the inspection. You're continuing then with capturing the data, with saving the data, and then doing the report. With having the report, then you can remove the scaffold again. Then you can bring the asset back to service. Then you're finished. With using the bike, you can cut through all this. It means you open the manway, you place the robot inside, you executing the inspection. By geotagging, you have the capability to tag the inspection data with the virtual model. And by this one, you can generate then the report automatically. That means all in all, we have a much lower risk. We assure API compliant inspection. We have high quality NDT. All that helps to reduce the downtime and the cost. What we see here on the bottom left part is the comparison. So typically that's an average vessel. So by saving all these kind of different steps, you're saving up to 70 hours in inspection time. Now, let's have a closer look at the bike, Robert.
Yeah, hi everybody. Um, I will go over this robot and some of the details about it. So the bike robot is a magnetic crawler vehicle. That means it uses permanently magnetized wheels to adhere to the metal surfaces on the inside or on the outside. And that comes with a couple of benefits. The first benefit is that if the system loses power for some reason, it will not lose contact to the surface. You can just basically, power can be restored and operations can resume. And the other thing is the magnet wheels are really strong, so it's a very reliable method of adhering to a metal surface. The bike has four wheels, a steerable front wheel section, and two rigidly mounted back wheels. And every wheel is powered by a brushless DC motor. What you see on the top is basically the payload. That is an inspection camera that can be tilted up and down. It comes with its own light. It has a HD sensor and 10 times optical zoom. It also features two laser dots for sizing, basically for figuring out at how big of a structure the camera is really looking right now. And it comes with a fully controllable lights, so to really provide the operator with the best visual quality. Then the other component on top of the bike, sitting here in the back, is the 3D lock visual LiDAR sensor. It's used for localizing the bike inside of confined spaces, and that is really helpful for data localization as well as for control of the robot. When it comes to control, this robot is equipped with a fisheye camera in the front as well as in the back. The cameras come with built-in LED lights for a wide angle illumination of the environment, giving the operator a really good view. These cameras are 180 degrees viewing angle and allow the operator to really see even the front wheels, the surface where the bike is going on, and avoiding any type of obstacle or other things, and finding the exact location where the inspection should be performed. In between the wheels is the final payload part. That is a ultrasound sensor. It's retractable, basically by springs. It goes up so that the bike can move. And as soon as coupling water is provided to the module, it goes down and provides a thickness reading of the surface the bike is sitting on. Now, here I summarize again a bit the features. It comes with a HD camera. This is the standard features. A UT inspection capability. It can manage the digital twin paradigm by localizing itself as well as the data. So it does not only localize the robot, but also where the camera is really exactly pointed at. It features the 3D navigation that helps the operator to achieve a safe operation, and all the data is stored properly in 3 dimensions. It's extremely mobile. We will come to that later. Can manage corners, flanges, can turn on the spot. The typical applications are pressure vessels, storage tanks, and large diameter pipes. It can go inside and outside of these pipes. Now we will see the bike in action on a short movie taken inside a real asset. Um, I will maybe comment the movie a little bit, but yeah, it's mainly to show you how it operates. The operator has a control station and a joystick. On the control station, he has a screen where he can see all the information. He does not have to go inside. He can just place the bike on the flange and then it can go inside. It deploys through top-down flanges or horizontal flanges or from bottom up. That doesn't matter because the bike can just stick to the surfaces in any direction. When the operator finds something of interest, he can basically capture the image. In this case, this is a visual inspection, and the data is then stored in with its location in the three-dimensional environment model for replay later for analytics and interpretation also offline. Because the bike is very mobile, it's capable of driving up to nozzles and really pointing the inspection camera inside the nozzles. And it can go down into a sump section of a pressure vessel, as you've seen here. The camera itself is high quality, in particular for distances between a few centimeters and maybe 2-3 meters, where the illumination is still really good. What we see here is the deployment of the ultrasound sensor, giving a thickness reading of the surface. The bike can obviously come out on its own, so basically no deployment tools are generally required. It's really just placing the bike on a flange and enter the vessel. In the next section, I will try to go into a few more details about the physical capabilities and also some limitations of the robot. So basically, size. The bike robot is fairly small. It's roughly 300 millimeters in length and 200 in width and height. Obviously, that depends on the payload that is mounted. This is just without the camera and the localization unit. It is a little higher with the payload mounted. It weighs roughly 10 kilograms. So that means an operator can quite easily lift it off the ground with two hands. That is a crucial thing to deploy it into a flange or onto a structure. The bike can move forward and backward at 50 millimeters per second. And obviously it can also go slower. The operator has very precise control over the speed and the steering as well. Now I would like to show the type of corners the bike can manage. We mentioned concave corners. These are where the bike has to go through an inner 90-degree corner. That is possible, and that it can also cross the convex corners, which are more often present, basically when deploying through a flange that is going over a convex corner. The bike can go through the flange, should be 400 millimeters, so that it can cross inside, and it can really manage this step from the tube into the asset without any problems. For inspections inside a pipe, the absolute minimum is a 300 millimeter or 11.8 inch diameter. That means the bike goes without any payload or only with very small payloads such as borescopes or other special sensors, or obviously the ultrasound sensor. As soon as the pipe is slightly more bigger in diameter, the bike can then also maneuver to the circumferential direction. It cannot do that in a 300 millimeter. In 300 millimeter, it basically goes straight. And as soon as it's a 600 millimeter pipe, then it achieves the full free maneuverability without any limitations. On outside pipes, it starts at roughly 400 millimeters, and again at 600 millimeters diameter, full maneuverability is achieved. A very typical way of deploying the bike is through a flange, as we've seen in the movie already. That is usually no problem. It's just important that the clearance is enough. So basically, if any add-ons are mounted, the diameter could increase slightly. In case the flange is built in such a way that it has it protrudes into the pressure vessel, so we call that it has lips, then that could cause some issues with the bike deployment depending on the height of the lip. I will show that here. So basically, when the lip is too high, then the bike will not be able to manage go over it, and then basically a special deployment bridge can be used. It's basically a metal bridge that gets attached to the flange that allows the bike to cross over. This situation requires slightly more clearance, so it doesn't really work on a 300 millimeter or 400 millimeter flange, but as soon as it's installed, it's also very safe. This is a special tool that, in case you should ever encounter this situation, please contact us. We can supply you with the tool. But very often the lips don't protrude that deep everywhere due to the radius of the surface. So there is often on the side, you can find a step that is not so high. The bike can manage a couple of obstacles. It can go over steps. Usually this in pipes and pressure vessels, these are diameter reductions. It can manage thin coatings, so 1 millimeter of paint, thin epoxy liners, etc. is possible. It can also usually go over small elevations, let's say bolts, something there. It really depends on the structure. Typically, an operator would avoid driving over such things, but it will not cause the bike to crash or lose contact to the surface. Also, small holes are not a problem. The wheels can just drive over them, and also small gaps can be managed quite easily. Loose particles like with a bit of rust and debris, they can accumulate on the wheels. In that case, the operator is advised to move only forward, and in case he wants to turn around, just do a forward spot turn. Like that, the debris cannot get under the wheels and cause the bike to lose contact. There are a few things that do not work with the bike. For instance, very thick coatings, thick epoxy, glass lining doesn't work just like that. Loose coatings, if the scale corrosion plates fall off when the bike drives over them, the bike falls with them. The same is for loose parts. Loose wires, washers should be avoided. They can get stuck on the wheels and hinder the bike from movement. Also, obviously, bigger holes and stiffener bars cannot be crossed with the bike. I will now show another movie. It's basically, again, inspection with the bike, and I would like to highlight a few other properties. So what you see here is the operator is basically preparing the 3D model by slicing the view open, allowing him to see where the bike is currently placed inside. This is basically just after the deployment through the flange. And then he can start doing the visual inspection, in this case, of a baffle plate. In the 3D model, the bike is represented as the bike, basically in its actual shape, and the payload is presented in a slightly different color, and the operator can really see where the camera is pointed at, and also like what field of view the inspection camera currently has. He will also have full control over the navigation lights as well as the navigation cameras, and has the entire context from the 3D model. Obviously, for doing the inspection, the operator will switch the screen in such a way that mainly the inspection camera is shown, but it's also possible to show the navigation camera instead. The camera on the bike has a controllable tilt axis. For the operator, this is quite easy. As soon as he stops the bike, he can basically tilt the camera, or he can also use some features in the 3D environment to automatically point the camera at a certain area. The panning of the camera is typically done using the wheels of the bike, basically the steering capabilities. This allows the operator to do this inspection without driving all around with the bike. That saves some time and makes the entire inspection way more efficient. The dialog that is on the screen now is the capture dialog. It allows the operator to annotate the findings, gives more comments, and even draw annotations on the images if he prefers to do that. All these functions are available in the post-mission data viewer as well, and every data point is stored with its 3D location. So, and not only that, it's also the robot location is stored with it, so that to interpret the data, you can also take into account from like how far away was this picture taken, for instance. Not every part of the environment is usually part of the 3D model that is done before. So it is very important also that the operator pays attention to the cameras when he moves the bike. That's also why the operators typically try to find a good spot for the bike to be from where they can see most. And then basically do a lot of the inspection from there and then move the bike again to another spot. Here you see the high level of detail that you can get with this kind of camera, and also with this very steady camera mounting. The robot just doesn't move. So with this, I would like to hand over back to Eki for some typical applications.
Okay, thank you, Maurits, for this quite good insight. Now, let's have a look at application domains. The application domains is quite broad. I mean, it's oil and gas, so onshore, offshore exploitation platforms. It's petrochemical processing facilities, refineries. It's on LNG, floating LNG plants and regasification plants. It's on tank farms and so on and so forth. It's used in chemistry, basically all the process, let's say, assets used in there, but also in power generation. Hydropower for turbine rotor inspection, for penstock inspection, or in thermal power plants for steam drums, one-through coolers, and so on and so forth. That means from industry-wise, quite broad in all kind of processing plants. So it's very much focused on, or basically suited for confined space inspection. One important notice is, or one thing, it's magnetic wheels. It's used on carbon steel or magnetic surfaces. So these are the application domains. Maybe some typical assets we have inspected in the past. So it's a dry gas vessel, for instance, electrostatic separators, gas scrubbers, gas separators, gas spheres, knockout drums, kettle type of exchanges. shell and tube exchanges. Typically, the bundle is removed for doing this inspection. Then all the steam systems, then all vessels which are kind of, let's say, prepared for non-intrusive inspection, or when this has been completed, and to provide additional information, and water seal rooms, and many more. So again, confined space inspection and carbon steel. So quite broad. And typically the customers who have the bike in their portfolio use it like a toolbox, or like a tool in a toolbox. If there's a need, then they use the bike to having a close inside look or doing ultrasonic inspection. We hope we have given you a little bit kind of insight in the bike robotic platform. And with this, we are open for questions now.
Yes, and for you to place your questions, please use the comment section, and the bike is on screen now, so for you to remind you of the parts that you might want to ask questions about.
So we leave it open for half a minute for questions. Otherwise,
Well,
I mean, if you want to learn more, you see here then where you can find more information on our website, Baker Hughes, Baygate Technologies, Robotic Inspection Bike, or just ping us on LinkedIn.
yeah, I guess we should leave a little more time. Typing questions can take some time. And as Eki mentioned, a lot of information is available on the website. Also some movies, brochures, data sheets.
And for those people, I mean, we will have a follow-up session next week, focusing then on 3D log, which is the capability to take the inspection data to the digital twin, or basically to the virtual assets to create a digital twin. So we'll give a more detailed insight to this piece, which we have a little bit touched today. Okay. So location's cool, all clear, all set.
Yeah.
Okay. So once more, I mean, if there's a question, reach out to Moritz or me via LinkedIn, or visit our website to have a look. There we have some use cases, we have some movie material, we have some fact sheets, and so on, additional information. Have a look at this one, and feel free, or basically we're happy to listen to your questions then based on this one. Okay.
Good. So
Good.
there seem to be no questions. Probably the was either too clear or too unclear. So I would say in that case we can close it.
Okay. Thank you very much for attending. It was a pleasure.